And I asked you who had done Markov chains, who hadn't done Markov chains, and some people said I have done Markov chains, some people said I haven't done Markov chains, and a lot of people didn't put their hand up. Okay? So we're going to... So this course isn't about Markov chains. Indeed, you could do an entire course on Markov chains, and we're only really going to skim the surface in a very superficial way, all right? But just do enough so you know what one is, and some of the basic properties, and some of the calculations that we're going to need in order to consider the kind of random version of a dynamic program, which is called a Markov decision process. Okay, so we've done dynamic programming, or at least some dynamic programming. Okay, we'll do Markov chains, and with those two bits combined, we'll have enough to step on to do Markov decision processes, a random version of dynamic programming. Okay, right. So are there any questions at this point before we get going? No? Okay. So let's get going. So yeah, we're going to consider Markov chains, and I'm going to start again, like with the tree example, very easy example. All right. So our introductory example is going to be snakes and ladders. Okay. So who here knows the game of snakes and ladders? Okay. And who here doesn't know the game of snakes and ladders? Okay, again, no one's putting their hands up, so I'm just going to assume nobody knows. All right, and everyone's too shy to say. All right, so this is a very kind of classic board game. I guess we've got quite a few people. I don't know where snakes and ladders exists around the world, but it's a very simple game. Okay, so the idea is you've got a dice here, okay, and you've got a counter, all right? And the objective of the game is to get the counter from the start square at 1, and it's got to progress all the way over to the end square, which is number 12. All right? So if I roll a 3, okay, then the counter will go 1, 2, 3. Okay? Now, the slight twist on the game is that if I land on a ladder, then I get to take a shortcut and I can go up to 7. All right? But if I land on a snake, like say at this 9, then I go all the way back down to 3. Okay? And that's it. All right? So I roll the dice. Let's say it's landed on a 1. I go to 2, but I've landed on a ladder, so it takes me up to 7. Okay? Then let's say I roll the dice again. I get a 2. I go up to the 9, which takes me all the way back down to 3 again, unfortunately. All right? Okay. So this is a Markov chain. A very simple example of a Markov chain. All right? Now, you've done a lot about Markov processes. In particular, you've done lots of things about diffusion processes, I think. Have you covered things about diffusions yet? Okay. Or at least you will. So you cover actually very complicated Markov processes, or somehow complicated. But you don't, for some reason, we don't teach the easy version. This is the easy version. Okay? So it's a bit like a dynamic program. It's a dynamical system, as in I basically apply a function to the state that I'm currently in, but there's some randomness in it. So notice the position that I'm at next is determined by 2 pieces of information. All right? The position that my counter is on the board and the random roll of the dice. Okay? So I'm applying a function to my current state and a random number, and that gives me the next state. Okay? So before we had a function that is applied to the state, an action, and no randomness that determines the next state. Okay? So here we've got rid of the actions, and we're just having randomness determine where we go next. All right? So is that answer clear? All right. So here we're going to let the state, just to make everything clear, the state here, x of t, the state here, x of t, is the position of the counter on the board after the dice has been thrown t times. Okay, this forms a process, x of t, on the, that should say positive integers rather than just the integers. Okay, and this is a discrete time Markov chain. Okay, We're going to just do a few quick exercises, and you can do some more exercises yourself at home on these. Ooh. And before I continue, like I mentioned yesterday, I'm only going to very superficially cover the very basic material for this, but if you want to know more, then there's a very nice book called Markov Chains by James Norris. Okay, and it's published by Cambridge University Press. Okay, it's about £30 or something like this. So, if you want a bit more background material, then that's fine. And also the SCwAF book that I mentioned will have some basic information about Markov chains in the appendix as well. Right? Okay, so let's keep going. So here, there's a notion of a transition probability. Given that the counter is in square x, we let pxy be the probability that the next square is y. All right? I.e., in other words, pxy is the probability that given I'm in x, the next state that I arrive at, y, is y. Okay? So the conditional probability, given I know I'm at state x, what's the probability I end up at y? Okay? So let's do some examples. What is the probability that I'm in 1 and I next end up at 4? Okay, so I'm in 1. What's the probability I end up in 4? So who thinks a half? Who thinks a sixth? And who thinks a third? Okay. Well, let's try that again with some people putting their hands up. Okay? So you have to raise your hand if you think you know the right answer. So who thinks the answer is a half? Okay. So 50% probability. Who thinks the answer is 1/6? Okay. And who thinks the answer's 1/3? Okay, good. Some hands. Great. Thank you. Good. Okay. The more you put your hands up, ask questions, and all the rest of it, the more you help me understand where you're at with the course. Okay? So it's really worth you participating in stuff. There's no problem with being wrong. There's no marks for being wrong. And even in your homework, if you get it wrong, I like to give bonus marks for having a good crack at it, at each question. Okay? All right, so the answer is a third. Why is that? Because, well, there's two ways of getting to this square 4. One is that I roll a 3, and I go 1, 2, 3. Okay, and that happens with probability 1/6. Okay, the other outcome is I get a 1, 2, 3, 4, 5. I end up at the square 6, and I go down the ladder to square 4. All right? Okay, so it's not this unique position for every dice throw that several random events can end up in the same state. Okay? Okay, so that is equal to 1/3. Okay? What's the probability I end up at 7? Okay? Is it, who says a half? Who says a sixth? And who says a third? Okay, good. Yeah, that's correct. So there's two ways of ending up at square number 7 from number 1. One is that I go 1, 2, 3, 4, 5, 6, I end up at 7, or I go 1 and then up at 7 as well. All right? And then finally, very quickly, probability that I go from 3 to 4. Okay, so now, when I say P3, 4, I mean the counter's here on the 3 now. All right, so actually now the counter's over here and it's left from there. All right, and what's the probability I end up at square number 4? All right, so the answer again is a third. I can go here with probability 1, 1/6. I get a 1 and go here, or I could get a 1, 2, 3 and end up there. Okay, fine. Right, that's enough of the answer being 1/3. Now, so I'll just do, from the next exercise, I'll get you to do A, B, and D. Well, I'll tell you what, I'll just get you guys to try these out yourselves. That's one of your exercises for this week. All right. Exercise for you to try at home. Not too hard. Okay. Right. But the next exercise is quite an important idea. So let's suppose that I start at square 3, and then given I started at square 3, I go to get square 1. I mean, sorry, I go at the next throw, I go to square 3. Okay. So I start at 3, then I go to 3. I'll stay there for one reason or another. I'm not sure if that's even possible. Then I go to 6. Okay. And then, given all of that happened, I go to 7. All right? Let's consider another possibility where I go from 6 to 7. I start at 1, then I go to 5, then I go to 6, and then I go to 7. All right? And then finally, let's consider the probability on the second throw of the dice. I'm at 6, and then I go to 7. All right? The idea of something called the Markov property is all of these have exactly the same probability. Okay? Why is that? Well, what we're saying here is that the counter so let's say the counter's at 6. Oops. Is my... Oh, yeah. Let's say the counter's here at 6. Oh, I've got a slight problem that there's a snake there. I should change the numbers here. All right, let's ignore that snake. Bye-bye, snake. Okay? Let's say we're at 6. Okay? If I knew that I went from 1 to 3 and then 6, and I wanted to know, given I'm at 6, I go to 7 next, does the route that I took to get to that 6 actually affect the chances of going to 7 next, given conditional on the fact that I'm at 6? Okay? Well, if I look at the evolution of the system, all that matters is that I'm at state 6 and the throw of the dice is such that I next end up at 7. Okay? So I throw a 1. All right? So it doesn't matter that I went here, 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 and then end up at 6. Given all of that happened, and then I go to 7, it doesn't make a difference. Okay? So notice that I can sort of summarize all of the information that has happened so far with the current state that I'm at. Okay? And I can just chuck everything from the past away. All right? Is that clear with everybody? Is that all right? So that is the main, most important property with a Markov chain, and it's called the Markov property. It means that the past doesn't affect the future given the present. Okay? And the way to think about it is to think in terms of this dice throwing, that the information that I use to give the evolution of this system is the current state, nothing has to do with the past states, and the random throw of that dice. Okay? So if that's not quite clear, I suggest taking a little bit of time for thinking about that point. All right? So this is quite an important point. Okay? You can also check this yourself. You can do the calculations here. For example, you could do the calculation for this probability you can write this out And I reckon each of you could do the calculation. So just using Bayes' rule here. This is what happens when I'm at. Okay. Oh, and I'll put a condition on there. Okay. You could probably calculate what these probabilities are. Given I'm at 1, what's the probability of being 1, 6, and then 7? And given at 1, what's the probability I then at 5 and then 6? And work that out and then convince yourself that that calculation for the whole thing gives you the probability okay? So do check that. All right? So in general, given that the counter is on a square, we will see that the next square reached by the counter on the next turn is not affected by the path that was used to reach the square. Okay? This is called the Markov property. All right. The next thing to convince yourself of, which isn't really an exercise, I put it as an exercise, but it isn't an exercise, it's just something to note, that convince yourself, and I said this at the beginning, that if you're given the current state of the counter, okay, so given the current square and the throw of the dice, then this completely determines the next square. Why? None of the past information or anything like that was used in order to determine the next transition, just the current state and the random throw of the dice. Okay?